Okay, people are still coming in, but I think we can sort of start with the introductions. So welcome to this webinar, which is on a subject that's a little bit different to our usual webinars. Usually it's something on soil mechanics, which of course is an important material. It's important in general and important to Optum, but there's another material that's also very important, some would say even more important, and that's concrete. And that's something that is very important to Optum as well. The program you see here, the little demo, is for our program Optum CS. CS stands for Concrete Solution, which is basically a pretty advanced program for design and analysis of reinforced concrete structures. So you build up your building and then do your analysis and design in that way. So this is our first webinar in this series on concrete, and I can't think of anyone better to give that webinar than today's speaker, David Oliveira. David is a technical director with Aurecon, and I think it's fair to say that David has spent most of his career working on soil and rock, but has also recently done some interesting work on concrete. Concrete and soil, of course, often interact, and I think we'll see some examples of that today. But the focus is on concrete. So with that introduction, I will hand over to you, David. I just need to switch to you.
Okay. All right. I'm just going to start sharing my screen here. Just give me a second, put in presentation mode. Can we all see this? Can we just confirm we can see this, Kristian?
Yes, that's very clear.
Well, thanks everybody for making some time during your day. I think it's probably around lunchtime, I would guess, for many of you, or morning, or just beginning of the afternoon. I could see actually in the attendees, there's some people from here in Australia too. We call Down Under. Kristian is familiar, which is a bit late for us. He is 10 p.m. in Sydney time, 9 p.m. in Brisbane time. So it's a bit later. So thanks very much for the interest and effort. As Kristian says, I have worked I say I have worked most of my career what I call ground engineering. I don't specifically say soil or rock. It's ground engineering and the interaction between ground and structures. And concrete is probably one of the most used materials, maybe behind water in the world. So it became a topic of passion of mine in the last, say, close 8 years, I say, and how we could enhance and work better together. So the topic specific of this talk is some of our experience we had with using high performance fibers in concrete linings for tunneling in Sydney. Sydney went through a boom, an tunneling boom in the last 10 years, where we had an enormous amount of tunnels here. I mean, very uncommon we experienced here. Just myself, I in the last sort of 5-8 years, I've done over 60 kilometers of tunnels, and all of these are lined with concrete of one type or another. And we're going to show some study cases here of some of the different types of linings we use. Here's a photo of one of our tunnels. We have done some very large span tunnels. You can see here's in this photo is a 4-lane tunnel. So it's, impressive spans that we have excavated. And you can see the top is a bit painted in black, but that's sprayed concrete. So without further delay, I will move to what we're going to be discussing. So it's high performance fibers in concrete. So I think it's important to bring the discussion why do we like fibers? Why we try to use fibers? How do they work? why it's so common and so the use is stronger in tunneling, probably more than any other industry. And we're gonna use two cases as examples. There's a Westconnex case, which is a road tunnel, and we'll focus on some of the enhanced capacity of very thin permanent linings using sprayed concrete. Here in Australia, we more commonly refer to shotcrete. But yeah, it's essentially a concrete applied pneumatically, like with we spray. And the other one is a Sydney Metro study case, which uses a different type of construction, TBM, and use precast elements. So, and we're gonna see how we use fibers, how we got confident that the fibers would address some of our bursting and splitting concrete capacity concerns, and some of the work we have done in the modeling space. A lot of the focus here is it's around the use of modeling and advanced modeling to understand how we can make better use of the materials we have to really push boundaries and optimize, but at the same time to not compromising on safety. So making having some confidence that what we are doing, it will really satisfy our targets. And we're going to show how we have done this through some large scale verification testing, where we test things in large scale and even almost in real application. So the use of fiber reinforced concrete has, a number of advantages over conventional reinforcement. So I put a photo here of a conventionally reinforced tunnel. And you look at this amount of reinforcement that goes in this lining here, which I'm not, I'm not by any means saying this is over design. I'm just saying when using conventional reinforcement, you can understand the amount of effort that we need to put to be able to place these reinforcement, on site in situ before we're gonna cast our concrete. You can see, people, workers, installing working at heights, and the time required to do this installation. So one of the main benefits of if we can replace reinforcement completely with fibers is that we can completely remove some activities that are relatively unsafe. I mean, it can be done safely, but if you can remove it, in the hierarchy of safety, if you can remove, is the best approach is to remove something that could be potentially be unsafe. So removing work at height, removing lifting operations, because some of these cages are very heavy, it's a significant benefit for construction. And by doing that, you also speed up construction, so you get program benefits. So you can achieve your construction programs in a better way, and consequently, no questions asked. You have some cost savings, and reducing steel, you save carbon. You reduce your carbon footprint as well, so you have sustainability benefits. So there's a number of advantages when we can use fiber and replace conventional steel with fiber reinforcement. And as a result of that, the tunneling industry has been pushing the use of fibers, probably more than any other industry. I would suppose. I can confirm this absolutely, but that's my feeling as a practitioner. And we have been pushing the fibers, not only using fibers, but using high performing concrete, high strength concrete with high performance fibers. And we're going to discuss a little bit the impact of what I call high performance fibers. When coming to sustainability, just an interesting graph here from a study done by a Brazilian group, Daminelli and others in 2010. So it's not quite a very new study here. Is that showing that when we try to use higher strength concrete, try to make use of stronger concrete to try to save on volume, to try to reduce element sizes, try to reduce thickness, the increase in binder content is not, well, it can be linear, but it's not directly proportional. So, for example, if we take an example that I have put here on the left hand side, if we increase, for example, a concrete that you originally thought you would use 40 MPa and you start using 50 MPa, the increase in binder content is 15%, right, on this graph here as an average. So we go here from about 350 kilos of binder to about say 410-ish as an average. Obviously, there's a range here, and it's variable and depends on a lot of exposure classifications, durability requirement. But as an average, and that's a large number, a large database here. So if by increasing the strength, we can reduce volume, or we can reduce thickness by a similar proportion or even more, you're certainly going to be saving in carbon footprint. So some of the benefits, we always think, oh, look, I might not need to use higher strength. But if you're thinking of using higher strength and you're thinking of optimizing your design in terms of thicknesses and dimensions and volumes, you may get the benefit, right? But there are some implications when you start using that, high strength concrete. You need to think about ductility and the implications, particularly when you're combining with fibers, which we're going to discuss very soon. So, but how fibers work, and we have really to change our mindsets when thinking about fiber-reinforced concrete, differently from conventional steel, where we have very well positioned bars. We know the exact locations, and we can estimate lever arms to calculate the effect of bending moments on on flexural strength and so on. The use of fibers is really put into the mix design. So what we create a new material, which is a composite material, where the fibers aim to improve its post-cracking capacity. So once the concrete cracks and we have fibers crossing those cracks, these fibers can transfer forces from one side to another. And they will also promote not only indirect tension, but they will also, by trying to hold the crack together, it also facilitates some arching effects on the tip of the crack, which can have some benefits. So when we think about, if we understand, and conventional reinforcement too, and it needs to crack to be able to mobilize the bond capacity, but essentially the whole concept of fiber reinforcement is that the concrete needs to crack, and we need to understand the post-cracking behavior. So immediately we understand and clicks that, look, linear behavior is not the case here. I really need to start looking on how this behaves post-peak, post-cracking, and understand, how it develops in terms of post-cracking behavior, and how we can make the most in terms of our analysis, where some of the linear analysis, conventional analysis will not really can be applicable, but it will provide you very conservative results or answers that, as I'm going to show in some of the examples. And here's some of the examples of the behavior of fiber-reinforced concrete that we can see in some of the design codes. And obviously one famous design code is the FIB model code from 2010, which was published summarized in a book in 2013. And the version of the 2020 version, I think, is about to come out, or has come out. I'm not so sure. But here's a bit of a description of the behavior of fiber-reinforced concrete from the FIB model code. And what we show here in the right-hand side figure is that we compare here some different behaviors, like direct tension on the first column, then in flexure, and then in more something that simulates more your actual structure. And what we're showing here is, obviously, depending on the amount of fibers and the type of fibers, once it cracks, you can have a softening behavior in tension, you can have a softening behavior in flexural, and you can have a softening behavior in your actual structure, for example, in a slab, as you show at the end here. Depending on the type of fiber and the amount of fibers, you can actually go completely opposite. You can have the strain hardening behavior in tension. You can have a strain hardening behavior in flexion. You can have a strain hardening behavior in your structure. The interesting thing too is that with fibers, you can have actually a mix that, when you test in pure tension, might behave in softening. When you test in axial, it may behave in hardening, and that's something quite intriguing. And particularly when it comes from flexural to the structure. And this is very important for one of the examples we're going to show, because then it's the relevance of the boundary conditions that might impose different behavior post-cracking. And I'm going to really focus in one of our examples. We're really going to focus on this, on a concept that we can get a lot of better ductility when we consider the appropriate boundary conditions and the appropriate applicable conditions or boundary conditions in terms of either fixities or loads. But it's important to, in particular when we're talking about high strength concrete, it's important to understand how fibers, how we get ductility with fibers. So the way that the fibers are most ductile, once the crack initiates, when they have the formation of a crack, which is the figure on the most left hand side, if we can manage if we have fibers that are strong enough to be being slowly pulled out from one side to another, is when we get the most ductility. So if we can make the fiber, so for example, this is an end hook fiber. So the most of the bond is given by the the little the hook at the end, which will hold it together. If you can slowly pull it out, that's when you're gonna get most of the ductility. If they start snapping, you start losing ductility, and that's an important consideration, because when you start using high strength concrete, if you use the same fiber on a low strength concrete and you use the same fiber, then you move to a high strength concrete, your fiber might behave completely different. Where it was ductile, being pulled out, the fiber starts snapping, and it's really important to understand, because that's where we need to consider that the strength of the concrete needs to be compatible with the strength of the fiber. So, some people may not really understanding. And look, and to really verify this, there's a lot of testing that we have to do with the concrete mix. We do, flexural testing, and we do round panel testing to verify toughness and so on. But this is a concept that we need to bear in mind, that fiber type and fiber strength needs to be, concrete strength needs to be compatible with your fiber type and your fiber strength if you want to maintain the same level of ductility, or even better, when we're moving towards a higher strength concrete. Here's an example. For example, until maybe some 8-10 years ago in Sydney practice, the very common fiber that we used to use was the one on the left-hand side. Is a fiber produced by a supplier, by the supplier Beckhardt, is a fiber called Drum Mix 3D. The numbers here mean the aspect ratio, which is the ratio between I'm escaping now, is the diameter, is the length, no, length, yeah, length to diameter, and the 35 is the length. And so both fibers here we see on the left hand side and the right hand side, they are both the same ratio and they are both the same length. But one, you can see here, has an extra hook, right? Well, an extra fold, and there's a significant difference in the tensile strength of this fiber. So when we started using concrete mixes that particularly due to particularly internally, where we're designing things that needs to last 100 years, right? And it might be less common in buildings, but in infrastructure, where we have to design tunnels that we had last 100 to 120, and we are moving now to mostly being the minimum 120. Concrete strength for durability, at least here in our practice in Australia, is that we don't use anything that's less than 40 MPa concrete. Right? And when we're looking at a 40 MPa concrete, there was a significant benefit when we started migrating from this lower strength fiber to these higher performance fibers with higher capacity, where we could mobilize a lot more flexural capacity of the concrete, and also engage these fibers earlier by having the extra little bend, because you can imagine if you have better bond, once they start cracking, and engages quicker because it has a better, more bends in the end hook. So we moved in here in our practice from using the ones in the left-hand side to the right-hand side. And there was a significant move, because it was very uncommon to use these very high-performing fibers, in particular in sprayed concrete or shotcrete, and also in long-distance pumping that sometimes we have to do when you're casting linings underground, that you have to pump very, very long distance from the surface. Having smaller fibers is also benefit. These 35 mil length fibers are considered smaller fibers. They have much longer fibers which can be used in different applications. So it's just to show here the difference between what we consider maybe a more conventional fiber with, with strength in the order of 1300 MPa to a high-performing fiber with, more bends in the end hook and strengths that are exceeding 1800 MPa. Some of the fibers we use in our segments now, and some of the examples we're going to show, we're using fibers of 2200 MPa, so really high strength fiber. But why we see fibers used a lot internally and maybe not so much in other places? I mean, one of the benefits we have internally is that because we also deal with the ground, we know that compression is something good for concrete. Tension is bad. So we try to create tunnels with shapes that will promote compression in our concrete elements. And obviously, when you have compression, you enhance your flexural capacity. So here's just a very simple example. On the left-hand side, we have a sectional analysis here, which have the regular interaction diagram, axial forces versus bending moment. And obviously, if you have very low axial forces, it will be, at the bottom of this curve here towards the zero, and you can see that the bending moment capacity reduces. So when you put compression, in a lot of cases, even plain concrete could be made to work, right? There may be concerns if it cracks, what would be the ductility, but when you start putting compression, even plain concrete may be able to work, and that's what promotes, facilitates us to use fibers internally, because we naturally force our concretes to get compression. And there will be other structures, arch structures where we will be doing the same, but it's very common internally. And the other benefit is that because we put things in compression, that compression has also benefits in ductility. And I'm going to show here, just showing this example, which was an experimental study done by two researchers here, Ian Gilbert and Stefan Bernat, in 2018. So this in the lab, we're just testing the flexural capacity of this beam. Is a 4-point a 2-point load beam or 4-point load beam, where we load, but we're also able to put the beam in compression, so we can investigate the benefit of compression in the flexural resistance. So when you look at the graphs on the next slide, the first graph on the top left-hand side is the one with zero compression. Let me see if, oops, what have I done? Is the one with zero axial compression. You can read here in the legend, zero axial compression, and you can see once the concrete cracks at about, say, 12 newtons per meter, there's a softening behavior. As it cracks, it drops significantly, picks up a little bit, but still primarily a softening behavior and this is a fiber-reinforced concrete. Once we put 2 MPa compression, it cracks at about, slightly over, so just above the 12 Newton per meter. But we are no longer seeing a very strong softening behavior. We're seeing something a bit more sort of rigid plastic, right? And we increased to 4 MPa on the top middle corner here, a middle column. And the capacity not only increased for the, close to 12 to 14, but it has increased now. The peak values have increased to somewhere close above 20 newtons per meter. And you see post-cracking, a little bit of hardening, it reaches a peak and then start, a descent. And as we increase again, the capacity increases further from 22-ish, 20 to 22 to about 25, 20. So we're showing here the benefit of having compression, not only in increasing the peak value, but also changing the way that the concrete behaves. And some benefits are even crack spacing, because obviously we will be talking a lot here about ultimate capacity, but there's no questions asked. We always have to look at the serviceability limit state as well, and always going to be looking at cracking. But one of the benefits too is that, if you have, instead of having one single large crack, we can have multiple smaller cracks. There's certainly a benefit in durability, because the effect of the crack width itself. So we'll move on then with this sort of preamble on the behavior of fiber-reinforced concrete. We move to some of more practical examples. And I'm going to show here the Westconnex case study, where we really investigated, and I'll explain why we went into that journey, trying to prove higher capacities in sprayed concrete linings and thin concrete linings. A lot of these tunnels are excavated in rock, and we benefit that a significant portion of our rock in Sydney is of good quality, fair to good quality. It's not poor rock. So we're talking here more or less about hard rock tunneling in essence, although the rock is not that hard. The strength here is only about 25, 30 MPa. So in the terms of strength, we don't consider hard, but it behaves like a hard rock tunnel, because to really make the tunnel stable, the openings, most of what we need is provide support with rock bolts. So the rock bolts are the main support for our rock tunneling in Sydney. However, the lining, the concrete lining, and that's why we can make it thin, has still an important component. So you can see here this example, how we design this linings is that we make the tunnel stable by rock bolts holding the bigger wedges and facilitating arching of above the tunnel. So the arching of the stresses when we excavate happens within the rock. So we create this reinforced rock arch, or even sometimes reinforced rock beam. But we cannot be putting a rock bolt every 200 millimeters or every half a meter. It's not practical. So we still need to provide something that will be able to hold smaller wedges, smaller rock blocks or rock wedges from falling off. Can you see the picture here? So if I was able to hold blocks F and C with a rock bolt, like I show in the right-hand side, if block A falls down, it will completely destabilize the rest of the rock mass, because it will create a void here. So once block A falls, block B will likely fall too, then C, then E, then you expose the size of F and C. Then it can unzip a really problematic effect here, right? So what the shotcrete is relevant here is to provide support between the rock bolts. So we use the shotcrete as a retention system to be supporting any loads or wedges, blocks that may be forming between the rock bolts, and by this composite system, then I can provide, I can satisfy that the tunnel is stable. Now, how we design this shotcrete? I mean, shotcrete or sprayed concrete, as I said, the name is sprayed. The nature of spraying means that I have to have a mix that's able to stick. Once I spray, it needs to stick to the rock, it needs to stick to the ground. So obviously we design with the intention of having a good adhesion or good bond capacity. And this good adhesion, good bond capacity, in fact, provides a lot of resistance for the lining. If I have good adhesion a good shotcrete adhesion or sprayed concrete adhesion to the rock, the only really kinematically feasible failure mechanism is by direct shear. So because like if the shotcrete is adhered to the rock with enough capacity, and this can be measured, we can measure adhesion because we can core samples and can pull out and can test the adhesion like you do adhesion of in buildings as well. If you have a mortar and you want to test the adhesion of that mortar to the substrate, you can core and pull them out. We can do the same in tunneling. But so if this is with a good adhesion, which we can specify the some numbers to try to achieve, the only possible failure mechanism is direct shear, which generally provides you very good resistance. However, if you lose adhesion, and how you can lose adhesion, well, you can have your poor spray. You sprayed on something that was not properly cleaned or washed, or by or some sort of chemical deterioration of the rock. If you lose the adhesion, then your lining will start behaving more in flexural, as you see here on this middle figure here with this dashed red line around it. It will behave in flexural performance, and it will also behave in punching, because this lining now is held by the rock bolts up, so it can have a punching failure shear through the rock bolts here. And this is the mechanism that we design if you are to assume that the shotcrete is unbonded. It became practicing in Sydney to address risks of potential loss of adhesion or bond in long term, that we completely ignore in the long term, obviously, in the short term, we still use it, but in the long term, we completely ignore adhesion, and we have to design our shockwave linings to be with enough resistance in flexure or and in punching shear. And by doing that, the focus really then changes from having a good bond or adhesion to the substrate to flexural performance, and that's where the fibers come in. If I need flexural, concrete alone won't give me that, so I need to have fibers or conventional reinforcement, if you were to put, that will provide that flexural capacity. And also thickness became important, really important, because when you have good adhesion, the thickness is much less relevant, because the adhesion is something about an interface. And so thickness doesn't really come into play very much. It comes for practical reasons, but in terms of having a good interface, it doesn't. But when you're talking about flexural, thickness become important. And when we started looking and look, if we have to design ignoring adhesion to the substrate or bond to the substrate, we started thinking that look, we typically would have used shockwave linings or spray concrete lines that are in the order of 80 to 100 millimeters, and that's relatively common practice even outside Australia. If you look at the Scandinavian countries, Norway, Sweden, and even Denmark, hard rock tunnelings with 80, 100 millimeters in fair to good quality rock is not uncommon. But if we were to design this on pure flexure, we started realizing that we might have to increase the thickness, and this is something that we really didn't want to do because it would bring the cost of our tunnels up, and we would increase the carbon footprint of our project. And then we went on a journey on how we can make this better. And one way was we started looking at really high performance fiber reinforced mixes, which use high performing fibers. But how we design these in terms of flexural, right? So the way this permanent lining, thin permanent layer works is it can make an analogy to a slab on columns. If you just think that these rock bolts are the columns and your shotcrete, their spray concrete, is the slab, if you reverse it upside down, if you put it upside down, it's very similar. So the way that was typically designed until a few years ago in Sydney is that we use an analogy to slab design, and more commonly we also didn't want to complicate that much. We use a lot of very simplified methodology, like the direct design methods, which has an empirical characteristic to it. You assume your slab is actually simply supported. You get the bending moment, but it is supported by rock bolts, so it cannot be just positive bending. It needs some negative bending. So we shift the whole bending moment curve by a certain amount, and that's where this empirical factor of shifting this curve up and down comes into play. And this will be available in some of the design codes in different countries. So for example, in the Australian design code AS 3600 or AS 5100, which is our bridge code here, will give you, for the type of arrangement we have here, that shift is about 0.65 go in negative bending and 0.35 goes in positive bending. And that's what we used to do. But there's a problem with this assumption, and this assumption is that we essentially designing this lab essentially from almost like a linear elastic viewpoint, and or perhaps even a quasi-plastic viewpoint that suffers from a fundamental problem that has also suffered from yield line theory, is that moment capacity is purely related to bending capacity. And in our case, it ignores that if we consider that we are making this equivalent to a slab, our slab is actually continuous. It's not a simply supported slab, and it doesn't finish on the edges of a shotcrete panel. It continues. We have shotcrete going, so when we call a shotcrete panel, it's a shotcrete that's formed by 4 rock bolts, which is similar to a slab panel. We have more slabs side by side that will provide restraint if one of these slabs is trying to bend and rotate. And that's where we started looking, hang on, what is done in other structural designs like slabs or bridge decks and so on, is that we started investigating this effect of in-plane compression. So if you have a continuous restraint and one of these panels tend to be loaded and start bending, the other panels will provide this in-plane restraint, which will generate, upon deflection and cracking, it will generate compression that will improve the overall capacity. So this will be clear in the next picture here. So once it cracks, and particularly if we assume that there's one crack that forms in the center and a couple of cracks that form nearby the rock post support, you will generate this in-plane compression of this line of thrust that can enhance capacity. But to prove this, we would need to do, nonlinear analysis, right? And to also be comfortable with this, we wanted to rely on very high performing concrete mixes. So for those familiar with fiber reinforcement, sometimes we talk in terms of toughness, or energy absorption. So we provided here some numbers for this type of test, which is the round panels, is 500 joules. In Europe, it might be more familiar with the FNAC energy absorption, which is a different number. It's probably 2.5 times this. So the equivalent of 500 joules with our RDP, a round determinate panel from ASTM, will be equivalent to maybe a 1200, roughly, FNAC panel. And also in terms of residual, post-cracking residual capacity, based on, on beam testing, which is discussing some European codes and also in the FIB model code. And this is what we call a C mode 4 for a crack width of 3.5 millimeters, greater than 3 MPa. So we start looking at these high performing fibers that I mentioned before. So that's what we specified. And we went on a journey of trying to prove that we could get high capacity by modeling and by testing. So we're going to show the modeling first. So the modeling here, so if you were standing down in a tunnel and you look up a tunnel that's formed by rock posts and shotcrete, this is more or less, the left-hand side here is more or less what you see. You see a number of different panels of shotcrete that each of these panels are held by a group of 4 rock bolts. From a modeling perspective, I can take advantage of symmetry. I don't need to model everything. I just took one panel here, and I only need to put one support because I have symmetry on all 4 sides. And as long as the load, I'm also comfortable with how the symmetry plays in terms of loading, because not every single panel will be loaded. Not every single panel will have a rock block being formed or a load. So that's how we set up the model here. See, the model is set up as one panel, and we do some calibration. So we do testing. When we're developing the mix, there are tests that are done in terms of the mix. It's not just simple compression. We do a lot more than that. We do obviously our compressive strength testing. We do indirect or the Brazilian testing to get indirect tensile strength. We do beam testing, and this on the right hand side is a beam test. It's a notched beam test based on British standard or the European standard 14651. And we can get a bit of the flexural performance from this result here. We did some calibration of our model on how the concrete was performed against this beam test. Here's a very quick snapshot of our constitutive model. It's a simplified version. We're just showing here on the middle here what to have the top letter A there is the left-hand side, and upside down is the compressive region. The right-hand side will be the tension. That's for plain concrete. So what we did in our modeling exercise, we replaced that tension component by the behavior of fiber-reinforced concrete, which is shown on the bottom left chart here, the A on the bottom left-hand side. And there are other benefits that we consider in our modeling too. When we have concrete, similar to soils or rock, if you have confinement, you have a gaining strength. So we also include the benefit of what we call biaxial or triaxial enhancement in concrete. Once you have confinement, once you have restraint, that will generate those compressive strength, those compressive membrane actions or in-plane compression that we discussed about. So we include that benefit of very similar to how it's done, in soils and rocks, where you have, if you have friction and friction and cohesion in a simple way. By the effect of having friction and confinement, increase the capacity. I'll probably have to speed up here. So this is some of our modeling results here, and the green curve is what we would have predicted with normal analytical solutions, and the black curve is what we predict with the numerical modeling when we allow this concrete to crack and the in-plane compression to develop. So you see here a significant enhancement. And similar values apply. Similar value here applies also for the SLS, right? So you see here an enhancement of about 4 or 5 times in capacity, or even more. And the actual failure here was the punching. In this particular model, was the punching of the load here. Obviously, when you see this amount of enhancement, like 5 times what we thought they would have, you get a bit worried. So we don't completely just rely on modeling. We go to the field to test. So we created these tests here. We simulate the shotcrete as it happens in the tunnel. But what we did is we cut a notch in the rock where we could put a hydraulic pressure bag. So you can see here on the right-hand side, so the orange is the rock. We cut a notch, we put the bag, we put a geotextile, a fleece, to such that when I spray the concrete, I can break the bone. So I'm not relying on this bone or adhesion to the rock. And I put my rock bolts, how they are supporting, typically supported in Sydney. And I load this concrete and I'll check how much is the capacity. So we did a few of these panels. And here's just some photos of this. So this is real scale. So we're using real concrete mix, real sizes, real thickness. And here's a photo of the pressure bags, the geotextile to force the bond, the machine applying the shotcrete or the sprayed concrete, and some of the cracking patterns where we are monitoring with laser scanning and also LVDTs to monitor the deflection of the central portion of the panel. And here's some of the results we got. So in practice, shotcrete, although we assume in design a certain thickness, in practice, we never have a perfect thickness. We always have a little bit more or a little bit less. So you can see here there's some variability in the capacity. But because of the thickness, it's mostly associated with the thickness. So if you see here, panel 2 is the one that had the lowest capacity, but it's still, if just 75 millimeters, and we are hoping to get 90 millimeters, with 75 millimeters, we still had about 3.5 times the capacity we would predict with conventional method. And we did some back analysis to also show, to reassess our concrete here. And what we confirm is that in all of these tests, it wasn't the shotcrete that was failing, is that a lot of these panels were getting pulled out of the rock bolts because the rock bolt was installed on the back of the shotcrete and not in the front. And our numerical model confirmed this. In our numerical model, we have a sharp drop here just because of symmetry. Once one bolt fails, all the others fail as well. So it dropped. But in reality, in our panels, is once one rock bolt failed, it could span, the panels could span to the next bolt. So just showing the benefits here. And what this result is that we could reduce the thickness from the previously anticipated 130 to something of the order of 100 to 110. And this meant a reduction in thickness of about 15%. This meant just in carbon footprint, there's 33,000 tons of carbon that we could save. And about 27,000 cubic meters of less shotcrete and also 10% of less reinforcement. Just these numbers, just material itself, provide a cost saving in excess of $11 million to the project, which might sound small, but it wasn't. This is a conservative number here, $11 million. And also has a lot of benefits because if you're using less material, you have less, trucks coming to your site and providing shotcrete, because these mixes, they are not batched on site. They come from a batching plant. So you have less traffic. So you have less carbon associated with the movement of trucks. So let's move to another example. Actually, I'll just see with this project, this mix and this design, we won a few awards. One was by the American Shotcrete Association, ASA, gave us the Outstanding International Project of the Year, and the Infrastructure Sustainability Council of Australia gave us Excellence in Economic Outcomes for Sustainability Outcomes as a result of our research and development, and that was applied in practice. Now let's look at something slightly different. So it's a segmental lining, and you can see here the precast elements that we're using in TBM tunneling. And the concern here was more busting and splitting of the segments and highly concentrated loads. You can understand why they are highly concentrated loads. Let's just get some understanding of the terminology here. When we refer to segmental tunnel lining, one ring is comprised of several segments, right? So when you talk about a ring, it's a number of segments together, and obviously the individual segments are here. Circumferential joints is what connects, or the interface between two rings, and longitudinal, or some people refer radial joints, is the joints between each segments. And this is a picture of the back of a TBM here. We install these segments as the TBM is moving. You can see the hydraulic checks of the TBM right at the front there. There's a very quick, so this is a picture from Sydney Metro. What happens is that even during construction, when you're erecting all these segments, there are obviously tolerances, and we never build a perfect circle. So there's always a tolerance in some rotations where these joints might not be perfectly aligned. They might be slightly rotated right from the start. And also with the loads, when you can think of the loads, because these joints is pure contact of concrete to concrete, right? We only temporarily use bolts to hold them together that are removed later. So once these joints try to rotate, you can imagine that upon groundwater loads, rock loads, soil loads, whatever the loads that are being applicable there, these segments will tend to rotate, and you have these high concentrated forces in localized areas, which will put your concrete in compression really close to these loads, and in tension when it goes down into the segment thickness. And this is more or less how these tensions occur in a highly loaded segment joint, right? So you have a compression near the top here and tension near the bottom here. And generally, using elastic theory, this is how they dissipate at about 80% of the equivalent depth. And this equivalent depth depends on the eccentricity of this load. So we had an issue on one of our City Metro cases. We were crossing very deep. We were 90 meters deep under full hydrostatic pressure. So actually 85 meters of water loads. And you can imagine that, if you have these water loads, it puts your segments a lot under compression. And we were estimating very high forces, about 4,000 ULS loads, 4,000 kilonewtons per meter of load, with an eccentricity of about 30 millimeters of the axis of the segment. When you put this in elastic solution, this meant that in this portion here, where it goes in tension, we are estimating tensile of 7 MPa, which was, maybe 20–30% higher than the tensile capacity of the plain concrete, which means that this concrete would split. If it splits, we need to do something. So the typical approach is you estimate what is this tensile force that I need to provide. So in this case here, I'm estimating by using conventional strut-and-time modeling, and I estimate that I need 750 kilonewtons meter at about sort of close to 0.5 of the depth of the thickness of the segment. This load, I'm putting here some equations that can be used as typical equations of this type of analysis. Means that if I were to use conventional, this is easily done with conventional reinforcement. However, not so easy to do with fiber reinforced only. And the question is, well, can we do fiber reinforced only in this question here? Because what happens is, if the concrete cracks, then I have to use a post-cracking capacity, right? So if I use a post-cracking capacity, and that's what I'm putting here in the last dot bullet point, a post-cracking capacity at small cracks, because bursting and splitting, we really need to work under very small cracks. We cannot really allow it to crack to big cracks. I would only be able to develop with a fiber-reinforced concrete if I'm using elastic theory here. I would only be able to develop a resistance of 150 kilonewtons while I need 750. So I'm 5 times under the capacity. And the question that we ask ourselves is, hang on, but this elastic theory assumes that this strength, it only develops at the same depth of the elastic region, of this, this equivalent depth here, which is all based on elastic theory. However, for the concrete, the fiber-reinforced concrete really to develop, I need to allow this crack to propagate in length, which might go deeper. And that was our question that we wanted to answer. And then we went through the same process. We do that, 3D non-linear numerical modeling with this constitutive equation that I show here. Also, I have to say too, I forgot to say before, is we use this smeared crack model. So once the concrete in the model cracks, it develops a crack, a plane of weakness at the right orientations, and all the plasticity that happens in the model is corrected to that plane where the crack develops. So that's those, for those familiar with structural modeling, it's called smeared crack models. So what we did here, we simulated the rotation of the segments, and we got to a point that we said, hang on, we don't think that the resistance is as low as we thought, like 5 times under. Our segment, our fiber reinforced concrete without conventional reinforcement is able to resist this. And we go through the same exercise. We so look, we are saying that the resistance is 5 times greater. We go.
David, I think there's something wrong with your sound. David, can you hear me? I think there's something wrong with your sound. I can't hear you. Yeah, I think it's.
Did I drop off? Did I?
Yeah, you dropped out. Now you're back.
Okay, all right.
Great. Thanks.
So what I'm saying, I'm not sure exactly where I stopped. We went to test these joints again on the lab, and we created samples of real sizes, and we put a highly concentrated load. So we loaded only a 50 millimeter strip. And what you see here in these samples is that these steel bits here are not confining the samples. They're just providing the base for the LVDT to be able to measure from one side to another, so I can actually monitor the expansion and the cracking of this sample. So this is not a confinement reinforcement here. It's just really the LVDT. You can see here the tip of the LVDT is just contacting a little disc on the other side. So we tested here, and again, we did back analysis based on these test results. Unfortunately, with the machine we used wasn't displacement control, so we couldn't really get much of the post peak, but we got a lot of the non-linear behavior up to peak, where it gets strain hardening, and where we got the peak, then the actual testing obviously failed more drastically than our models, but we could represent the cracking pattern very well, and we could represent up to peak very well. And then we compared to our predictions, and we made here a comparison between our predictions and what were the testing results giving us. And we were, again, demonstrating that the fiber reinforcement alone could provide the resistance that we originally thought was 5 times lower. The main difference is that instead of limiting the depth of the crack to about one segment depth or thickness, the crack had to develop much longer in the ultimate limit state. But by allowing that and happening obviously with acceptable crack width, we could then develop the strength that we needed. So just some final remarks here. I think I went a bit over already. Is that conventional design methods based on linear analysis do not really fully or adequately represent the behavior of FRC, limiting the benefit of when you're using FRC, fiber reinforced concrete, as a solution. So nonlinear stress modeling, and particularly when it coupled with verification assisted by testing via large scales like we did, or large scale lab testing, provides really valuable method to understand what your problem is and what we can achieve with fibers, and really obtain cost-effective solutions. like we shown in these two cases. So both the shotcrete case or the spray concrete case and the bursting case, we demonstrated that fiber alone with no other reinforcement had capacity in the order of 5 times greater than we originally thought when we were using conventional design methods. And that's it for tonight. Thank you all for today.
Thank you very much, David, for a very interesting presentation. We are open for questions, and you can either raise your hand or type in your question if you like, and then I will. I think David can see them as well. So whichever way you prefer, and if you raise your hand, I'll put you online.
Yeah, I will answer the question by Reza here. It says slide 19, how the improvement of constitutive behavior of the steel fiber reinforcement due to confining pressure was shown. I might go
show
back.
sort of the failures. I think you show a failure surface which is sort of relevant for plane stress, but I'm assuming you use some sort of general 3D more Coulomb type.
So the constitutive model, if you look at this, let the B on the top right hand corner there, that's a biaxial stage there, but you also have the triaxial stage. I've only shown the biaxial here, which is because it's more familiar. It's a more common use. But if you see here, the B here is actually in biaxial state. So once you get the other confinement on the other direction, you have an enhancement of your compressive strength. So that's what that's a famous simplified model by, I think the name is a German researcher from quite old 1960s, so Kupfer, 1960. So that's how the biaxial or the confinement enhancement is included in the model. How it develops in the modeling is just a pure result of the boundary effects, right? So you have obviously symmetry planes here. So once it tries to deform laterally, but it's restrained, it start developing stresses in that direction. But in the constitutive model is using these biaxial and triaxial enhancements that you have equations also available in design codes like Eurocode or Fib model code.
David, the amount of fibers, you settled on some fiber count.
Yeah, absolutely. So for this thin shotcrete lining with the high performance fiber, we were not using. Some people will get surprised because they might be thinking high numbers like 50 kilos or per cubic. Now we use only 35 kilos of fibers per cubic meter.
Yeah.
So, and then for the segment, we're using only 31 kilos of fibers per cubic meter. So it's quite small numbers. It's hard to get much below those numbers because then you start losing the fiber network. So you need a certain amount of fiber to, to get, once a crack develops, to be confident that you have fibers available to cross those cracks, right? But 30 to 35 has been a number that has been very successful here. For shotcrete, more in the order of 35. For segments, we are going like in the 30s.
Yeah. Okay.
Someone asked about fires. Yes, one of the main drivers for this design was actually fire. We do the same thing here. We do analysis where we do we do thermal modeling, and in some of our tools that we use, we have the thermal modeling and all the degradation of the effect of temperature has on reducing compressive strength and reducing tensile strength and reducing modulus. This all comes in. So we put the thermal modeling and we apply it's a coupled analysis. So we apply the thermal modeling, then we apply the load, and we see how the model behaves. And also we do fire testing as well. So we test all these mixes. I must say they have also the steel fibers for flexural performance, and they have polypropylene fiber for fire performance. So there's the micro PP fibers that melt and then create connectivity of pores, so the expansion of vapor is able to escape and avoid spalling, right? So they also have PP fibers. PP fibers in our shotcrete was about 1 kilo per cubic meter of micro PP fiber, and in the segments are in the order of 1.5 kilos of micro PP fiber.
Just one more question about the fibers. What's the cost of these fibers? How does it affect the cost of the final product?
It's in
5
tons.
kilograms. Yeah,
It's in tons. I'm not a supplier, so I don't get much involved in the cost, but as far as I know, it depends on transportation. So in Australia, a lot of these fibers they're not produced here, so there's a shipping cost that adds. It depends, but certainly one of the things we notice when you compare, if I can give you exact numbers, I know it's in the order of like the tons is over $2,000 per ton or something like that. But I can't give you the exact number. But when you compare the high performance fiber to a more conventional fiber, all we need to do is to reduce 5 kilos in the fiber counts. It would pay for the higher performance fiber. So with the conventional fibers, we are using up to 45 kilos. When we manage to drop to 35 kilos, that more than paid for the extra cost of the high performance fiber and actually provided savings.
Yeah. Okay, great. David, we have a raised hand. I think you have the control. So
where do I see?
Under attendees.
Okay. James, is it so? Allow James. Okay.
Yes,
allow
yes,
here.
Yes.
Yes, because you for your constitutive relationship intention, you have a volume description because it's a relationship between strains and stresses. But when you have cracks, it's an area phenomenon, and that means that we get what's called size effects, and that also means that, for instance, the energy dissipation will be dependent on the size element of the size of the elements.
It does, yeah. So when we discretize,
you have to be really careful if you change the sizes of these linings, because you'll get a different results. If you make smaller elements, you'll get a larger load-bearing capacity.
Yes, you're absolutely correct. So these models are it is mesh dependent. So you have to do some calibration, and you have to be careful that when you calibrate, then you are using the same mesh elements. Yes. So the strain is calculated by the characteristic length of your element divided by the crack width that you are trying to calibrate against. So, for example, all these strains that you see in this slide here is actually related to a crack width and a characteristic strength, which is dependent on the model. So yes, you're correct. We have to be careful that this is adjusted for your element size. Every single time we do, we have to adjust, and there's always a process of calibration. And then when you ask the calibration, then you go to your real model, you have to use compatible element sizes. So there is an element dependency here, indeed.
So the final element is doing this calibration by itself.
No, look, when we my approach, obviously people have different approach. So I generate the mesh, I see what's a reasonable mesh size. Then when I'm specifying these strains here, I'm calibrating against a certain crack width that comes from the beam testing. Then I do the correction of the model at that point. Once I know the mesh size that I want to use, I do the correction of how I input these constitutive, it's almost like a piecewise discretization of the curve intention, and it's linked to the model size. So I know the model size first, then I do this, then I run, say, a beam test to calibrate, and I see if I'm calibrating the beam test correctly based on that. So for example, like I have shown here in this one, for example, right? So for example here that I'm calibrating and representing a lab test. So once I'm happy that this has been represented a lab test, then I take it to the larger model, and the larger model has to have similar element size, same element sizes as I have calibrated.
Thank you.
Great. We have another couple of questions, David. Can this be used for cut and cover tunnels? So more of a rectangular shape than a circular shape?
Yeah, look at,
Any-
obviously you can always use fibers to enhance something. I mean, a lot of the we don't have most of the codes we use for pure fiber reinforced are European codes. Here we use the fib model code. The only code we have in Australia is fiber together with conventional reinforcement. So obviously the Australian code is already thinking of those cases. I mean, you know, how are we going to use it? I think it really depends. So for example, deep beams, you're still going to get, you know, some deep beams, you're going to get compression, you know, you know, well, if your structure has restraints, for example, if your slab if you have say a tank structure, tank cut and cover, and your slab at the end has some restraints, you know, all of these you have to consider. You could, obviously, in more conventional structures where you have less compression, things become a bit trickier, but it is possible in principle. So for example, where we say rectangular shape, if you look at our Westconnex case, the line is flat, so it's not really arched. But you know, we took into account this restraint, your bounding conditions. Obviously, when you go to the edges of the lining, things change a little bit, and we look those panels close to the edge of the lining a bit differently. But if I am to maybe just show the picture here, if you see here, you know, those lines are really flat. So we design like slabs, right? So yes, you can use for non-arched structures, and we have, like, one of the examples is not really arched. It's generating compression by the fact how it's cracking and mobilizing in plane compression. I see here a question from Jiansu. For Westconnex, you showed lab testing results. It's about 4 or 5 times higher than the original. Did you apply a partial? Yeah. So these for the compressor here, they were all on factor. So once we factored, and one of the things we do a bit conservative here in Australia is that when we are factoring fiber reinforced concrete, we're still treating it as plain. So instead of using, which, you know, could be questionable, I mean, we could be a bit more aggressive, but because we are doing this, we decided to be more on the conservative side. We apply reduction factors to the strength that are the same as plain concrete. So we use reduction factor of 0.6. So yes, everything is those are comparisons that were unfactored. Yeah, it was, you know, we just wanted to show raw numbers so we can get an idea. But the raw numbers apply to both, apply to the conventional method as well, right?
So the factor 4 to 5 still applies?
Yes, yeah.
Okay.
So if it's allow for cracking and distribution for bursting, yes. How do you check so in the model, I can get crack width. So the model is, as I said, a mere crack model. Once it cracks, the model puts a plane where all the plasticity will be corrected based on, you know, deformations in reference to that plane, and how much that plane, that crack or the plane of weakness start opening will start giving me the development of the crack width. So I can get as an output crack width. In the testing, I measured those too. So when I said that I allowed the crack to develop longer, but if you look here, if you look at the test results, so I'm going to put it back there, we are still talking about here. You can see here the developing, even in the testing, the result of the crack opening here were the peak strength were in the order of 0.5 and 0.6 millimeter crack. Obviously, for this is ULS, right? And that's why I said with bursting, splitting, the cracks you work with are smaller than in flexural. So this is in ULS, and that's where, you know, it's a reasonable number actually to compare 0.5, 0.6 millimeters. A number of researchers have found that this number is indicative of a potential peak, you know, peak value. That's So in here we measured in the model, we can directly get it from the model what it is. Obviously, this is ULS. In ULS, these cracks are so we designed it to work smaller. So generally we're designing fibre-reinforced concrete. We have been working in Australia with an allowable crack width of 0.2 millimeters in our tunnel linings.
And I think that was the last one, David. So
yep.
Thank you very much again, and thanks to the attendees, and thanks for your questions. And a video of this recording of this webinar will be available shortly on the Optum CE YouTube channel, and you will get an email about it as well, I believe. So we will have a webinar soon again. And I believe you'll be notified about that as well. So thanks again, and see you next time.
Thank you. Cheers. Thanks, everyone. Bye-bye.